Welcome. This is a new lesson, and in this new lesson, we will shift to from a single variable derivative. So basically, like what we did before, we have like a function like f of x, yeah. Uh, but now, what we will do now, we will have a function that is multivariable. So it will be like function f of x, y, z, and t. So that could be like concentration that is changing in x, y, z, and t, like three-dimensional space and time. That could be head, hydraulic head x, y, z, and t, or not necessarily. This could be like any number of variable. I'm just giving you this because this is something that you, or temperature. So that could be here. That could be temperature, concentration, hydraulic head, whatever, yeah. And this lesson, it will be like a little bit more on the math side because the idea of it, I want you to get some basic concepts, basically like the main basic concepts and or conceptual understandings that I want you to get is the difference between like total derivative, for example, dy over dx. That's what we did before, versus like partial derivative dy over dx. So that's like one of the main concepts that I want you to understand like the difference. That we will be do this in part 2. But before we do this, let me just give some introduction about uh, before we get into this, I will just give some other topic that I would like to cover. So here, this is again like example of multivariable. So here you have like head with it changing in space. So this is like three-dimensional space. So this is a groundwater flow model. You have your hydraulic head. This is what's plotted here and how it changes in space. And this could also change in type. So we want to understand like this changes. And that's why we are actually studying calculus, because calculus is all about these rates of change. So we want to keep, that's how we study the system. But okay, so let me start like part 1 of this lesson. So basically, like this lesson, you'll learn some concept that we will build on later on. So later on, we will build on this concept of like partial derivative when we get to vector calculus and when we get to differential equation. So here, for example, like this guy is, you can describe this guy with a differential equation. Maybe that looks something like this. The h sounds like storage coefficient here that would be equal to d over dx k dh over dx, something like this, yeah. So you see here, this is like a partial derivative. So that's like multi-variable. Yeah, I have something that's changing in t and x. Okay, so I will start with parametric equation. And so basically, like in this lesson, I will cover three things. I will like, for multivariable function, I will cover parametric equation, I will cover partial derivative, and I will cover implicit differentiation. I could have just did like partial derivative and like ignored these two. The reason I am including these two, because remember I promised you that we will be practicing for your FE exam, and in the FE exam I noticed that they include parametric equation, so I said, okay, why not cover it? And in the FE exam, I noticed they provide you with some exam problem that is easier to solve with implicit differentiation than with partial derivative. And I will show you these problems. I will give you a problem and I will tell you do it with partial derivative and do it with implicit differentiation, and you'll find this is much easier. This might take you, I don't know, 5 minutes to solve it, or maybe less than, like this will take you like 1 minute to solve it with this method. Yeah, so that's, so basically that would be more like math things, mathematics things. This would be also more like mathematics thing. Yeah, so this is more like math, this is more like math. Yeah, But this is important for conceptual understanding, like partial derivative, which we will build on later. I don't know if this makes sense or not, but here, part one, we will just do parametric equation, simple and easy stuff. So parametric equation are function where variable are expressed as dependent on a third variable parameter. What does this mean? Well, this is what it means. So let me read this. So just listen to me. Instead of expressing derivative of a function, so I have a function f of xy directly in terms of independent variable like x and y, express the derivative in terms of a parameter, say s, which govern the behavior of both x and y such that we can get like x would be like a function of s, this like extra parameter, and y would be a function of s, this extra parameter. So my f of x would be something like this. X as a function of s and y as a function of s. Oh my god, what does this mean? Yeah. What on earth does these things mean? It sounds like not very clear. Okay, so maybe let me, I think to get, let me just give you, maybe if I give you like some example that might make things clear. Like, so let's just assume, you know, for example, like there is like a river, something that looks like this, yeah? And for this river, let's just like assume that what can we do for this river? For example, like just trying to come up with something with like a good explanation. Yeah. So let's say you have like some contaminant that is like flowing across this river from upstream to downstream, and this contaminant. Uh, the concentration of this contaminant, it changes based on the width of this river. Yeah, so here like based on the width of this river. Okay, so we have like our first uh, independent like variable would be like, let's say, concentration, and our second one will be the width. So how could I find like a function of like concentration? How concentration is it changing in width? How could I find this function? Well, actually, we don't know. Like, we don't know how concentration is like it's changing with width, and we actually don't need to know, yeah? Because what we can do, we can use something called like parametric equation. So basically, I can express, let's say this is like a distance, like s here. Let's say this is like a distance, like a third parameter. I just introduced like a third parameter here, s, and I could say like the concentration of as a function of s, like how concentration is it changing as like these things like this blue move like downward, and also I can express like w, like the width of the river, how is it changing as uh, as like from upstream to downstream. Yeah, so basically like I don't need to know this guy, but I can just simply say, okay, cs, for example, that's how this concentration is changing. I could say like, I don't know, just making anything up. Yeah, something like this. Yeah. So it follow like an exponential decay. So this is S here. Like you see, this is my new parameter that I introduced, like this new parameter, this third variable that I introduced, like S here. So basically the concentration as a function of S, as S increase, you have like this exponential decay. How the river width change with S? So I don't know, like you can make like, you can say 5 plus 0.1 s, for example. So it gets wider as this distance increase. Yeah. Okay. So now my question to you is how, for example, like how could I find how the how the concentration is changing in with widths. Yeah, how the concentration is changing in widths. Well, I don't know this equation. I don't even know an equation between concentration and widths, and I don't need to know it because I know another equation, which is concentration in terms of distance, like like with this parameter, and I know in equation concentration with respect to like a third parameter, which is also distance. So how, if I will tell you like what is the concentration is changing in width, you know what? I can do a trick. To remember the chain rule, I can do a similar trick here. I can say, well, I can say like concentration, like this guy with respect to S, and this guy with respect to X, because like I can cancel this guy with this guy. Yeah, do you agree? Undo. So basically, I just did a trick. Like I don't know this function, but even though I don't know this function explicitly, I could still find how the concentration is changing with width because I have introduced a third variable, which is S, and then I can know how concentration is changing as we go down and how width is changing as we go down. And then basically that would be like, that's how I could find this rate of a change. Something like this. I mean, why am I teaching you these things? Because I mean, originally I didn't want to include parametric equation. I didn't thought it's that important, but since I found it in like the FE exam, I found like it's like they include one of these things, so I just included it. Yeah. So let's do this is so here this is an FE exam problem. So that's what I found. This and said, okay, why not cover it since I promise you to do this thing. Yeah. So I'm basically telling you what is dy with respect to dx. Yeah. And I'm giving you an equation for x and I'm giving you an equation for y. I don't have an equation, I don't have a function of y and x. I don't have like this or x and y or whatever. Yeah, x and y or y and x. I don't have this function. I don't have this explicit function, but I don't need it. I can still find this derivative even though I don't have this function because I can just make a trick. I can make say dy over dx. Here's my trick. That's equal to dy over ds divided by dx over ds. And can I do this? Yes, of course. So here dx with respect to ds, that's equal to what? That's like 2s plus 2. Yeah, that would be equal to 2s plus 1. Yeah, and like this guy here, dy with respect to ds, that would be equal to what, like 3 minus 2s. Yeah, so I got something like this. So what will this give me? So this will give me this guy here, 3 minus 2s over 2s plus 1. Yeah, that's what this give me. And finds the slope. So basically it's telling me finds the slope for s is equal to 1. So the slope, so basically like I substitute here x is equal to 1. So that's like 3 minus 2 divided by 2 times 2. So I get here 1 over 4. So the slope at s is equal to 1 is like 1 over 4. That's like an FE exam. So now you know how to solve these things. Get a grade and easy grade. Yeah. So that's like in the FE exams, that should be an easy grade. Okay. Here is a practice problem, again an FE exam problem, and try to solve it in your own. That's a be good practice for you, what you learned in the previous lessons, and this is like the solution here. This is something you should know for trigonometry. Like, do you need to know these things for like the final exam? No, you don't. And the final exam is also open book, so you can get these things. Yeah. Just in case you don't remember from trigonometry, sine theta over cosine theta is just like tan theta. Okay, so that's all for this lesson, and see you in the next lesson, which is the important one, and it will be long.